The fourth drill video. Today we're going to cover some stuff on NA data, missing data. We'll talk a little bit about factors, and then we'll talk about the binomial distribution and some column renamings, and then a little bit of ggplot at the end. So just get right into it. First we'll load our tidyverse library, which we always have to load. And then we're going to run this line where I'm reading in this data frame that I found into an object called NA data. And if we look at what NA data is, this is just a really good data set for demonstrating NA. So here we can talk about a few things. So first of all, we notice that we have this monthly charges column that's a double or numeric column that has 3 NAs, or rather it has 2 NAs and 1 NaN. So that NaN just means not a number, whereas NA means not available. There is not a data point in that particular spot. So not a number means that there is something there. It's not that it's missing, but whatever's there can't be computed. So 0 divided by 0 is going to be not a number. They get treated the same though as far for our intents and purposes. So just don't worry if you see something that says NaN instead of NA. Think of it as the same thing. But then you notice here in this column, for total charges, it read it in as a character column, and it only has one highlighted actual coded NA value. But you can see that it also has these other two lowercase na and n/a here, that neither one of those got read as actual NA values. They just got read as characters, which made this entire column into a character column. So we'll get into that. And then also you see here on this one where they have like just a couple dashes, which should be NAs. It's missing data, so we're going to go over how to situate these missing data, and then what are the effects of having that missing data in some of the functions that we're using, and how to get around that. So the first thing, as far as this total charges goes, again, it's just that because they're, the capital N, capital A is the NA proper in R, it recognized this one entry, but not these other two values as NA. But if we just use the function as.numeric and run that total charges column through as numeric, then anything that's not numeric is coerced into a numeric value. So if we just take that NA data, the tibble, and pipe it into mutate to change the variable total charges equals as numeric of total charges, and you can see now, after doing that, those two other n/a and lowercase NAs were both made into like actual NAs that are recognized by R, and the rest of our column is now numeric or double. As far as creating factors, at its most basic level, you can just throw in a variable into this function factor, and go from there. Now I want to point out that here I'm using the base R $ notation, because here in a minute I'm going to be switching back to tidyverse notation, and I want to make sure that I'm going to try to do a better job of making that distinction clear, because it's easier to see certain things when learning this new function in this view, but then as we string it with other stuff, when we actually are creating these factors and using mutate, you don't use that $ notation. So this is just for explanation's sake that I'm using this $ notation here. But if we want to factor this churn variable, which is just a character vector or a character column, and it's just no's and yeses, and if we just run that in factor, then what it's going to do is it's going to convert this into a factor, which its levels are no and yes. if you wanted to change the order of the levels and make the yes the first level and no the second level, because that kind of thing will become important later down the line when we're looking at certain analyses where we're looking at categorical factor variables, and what gets used as the reference group will be the first group. And so if we wanted to switch that around, then inside factor we can just tell it that we want to change our levels, and so we'll order it yes and then no. And so if we run that line, we can now see that our the values are the same, but now yes is recognized as the first level and no is recognized as the second level. And then finally, you can also change the labels, so when you're looking at a factor, these actual yeses and nos here are the labels, but underlying them there is a level order, so the first level, second level, third level, etc. And so if you wanted to change the actual labels that are associated with those levels, you can add an additional argument of labels equals. And so in this case, you can see that when I just make this exaggerated yes and no, that's what it changes these values to for this churn variable. So if we look at if we look back and see what our NA data frame is here, and if we look back at making that factor or this payment method into a factor, you see that it gives us these levels, this double dashes, bank transfer, credit card, electronic check, and mailed check. But again, we don't want these double dashes to be recognized as a character, as a level. So instead, if we put the argument exclude, and exclude then in quotation marks these double dashes, what this factor will do is it will just turn those two missing places with the double dashes, it turns those into NAs. And so now if we add all of these things together, we start here with the NA data frame and we pipe that into mutate, because we want to mutate and change or create variables. And so we'll say our total charges equals as numeric total charges, churn equals factor churn, and then payment method equals factor payment method, but exclude those double dashes. And so notice here that once we are working inside mutate, once we are inside the tidyverse functions, we don't use that $sign notation. Once you pipe in the data, it knows what the reference for the variables that you're putting in, or it assumes that it is the data that you are piping into the mutate function. And so if we just run this, it will take the monthly charges or total charges column, does the as numeric so that it forces those mislabeled NAs to actually be proper NAs. It converts churn into a factor, and then also converts payment method to a factor, but then takes out those two that were just the double dashes. So now we have all of the actual NAs properly identified in R as NAs, but because I just highlighted and ran it and I didn't actually run this assignment arrow, it still hasn't changed. So if I just look at NA data, it'll be the same. But now that I run it and store it over NA data with this assignment arrow, now when we look at NA data, it actually has these NAs in that data appropriately. Now, as far as how NAs affect your analyses, it varies from function to function, and that's one of the reasons that Bill and I kind of joked that missing data is going to be the bane of your existence in data science and data analysis, because it really can be quite a pain, because there's not just one way that's the right way to do it, and there's not just one way that the functions all use. So the first thing will be in some of the base R functions. So like if we're wanting to use just the mean function and get the mean of this monthly charges column. So we would just take our data, NA data, and pipe it into summarize, and we want to create a column called m.monthly, which is the mean of monthly charges. But when we run that, it returns NA. And that's because as soon as this function hits an NA value, it can't compute that mean, and so it just triggers everything being rendered NA. So within the mean function, if you add the argument na.rm equals true, then that's telling it to remove those NAs, and now when we run it, it will remove any NA values that exist in that column and go ahead and get that average. Same thing happens with the standard deviation function, that if we just run pipe our data into summarize, SD monthly equals SD for standard deviation of monthly charges, and it outputs an NA. But if we instead just add a comma and na.rm equals true, then we will get that standard deviation. For the core function, things are a little bit different. If we try just to take our NA data, pipe it into summarize, core, monthly, total, so this is just the correlation between the monthly charges and total charges. And if we try to run that, again, it's going to tell us NA, because when we look at this data, it's going to hit these NA values, and it can't compute a correlation there. So when we look at the correlation documentation, we can see that core doesn't have na.rm equals true. Instead, it has this argument use equals, and there are a few different arguments that you can put in there. So if we put in the same thing, we take our data and pipe it into summarize and create a column called core monthly total. That is the correlation between monthly charges and total charges. Use equals pairwise complete obs. That's pairwise complete observations. Then now we get that column core monthly total, and the correlation between those two is 0.813. So what that's doing then is it's taking only the pairwise complete observations. So when it looks at monthly charges and total charges, this first pair is complete, so it's included. This one is missing a value, so row 2 is kicked out. Row 3 is missing a value, so it's kicked out. 4 is good. 5 is missing a value, so it's kicked out. This one's kicked out. This one's good, etc. So anywhere that it has both pairs in whatever variables you're putting into the correlation get included in the correlation, and if there are any missing values, then it's just excluded. That pair is excluded. And I just wanted to also point out that the use equals is actually a partial matching, which I briefly talked about what that meant last week. But so instead of using pairwise complete obs, if you just type in pair, or for that matter, literally if you just put use equals p, then it will assume that you're talking about pairwise complete observation, because when you look at the other options, it's everything, all.obs, complete.obs, na.or.complete, or pairwise complete obs. So because there's only one argument that starts with pair for use, if you type in pair, it will assume you mean pairwise complete observation. So just to point out that you can just say use equals pair if that's easier for you to remember than pairwise.complete.obs. So moving on to the next thing, we're going to read in some data from the class website. That is the wages data. And so if we just take a glimpse at what this data is, we can see that we've got 2,901 rows, 14 columns. And here are the column names: X1, year, age, marital, etc. We can look at our column types here and like those first values of each column. So we've already seen this in today's script, even up where we did as numeric. But so just want to remind that there's a lot of different as dot whatever functions that coerce variables into specific other data types. And then there's the is dot whatever functions that are the logical functions for testing if something is, whatever. So we have as character, as numeric, as integer, as factor, if you wanted to coerce something into one of those types of things. And then is dot character, numeric, integer, whatever, to return a true or false for, is something a character vector. So if we use is.character for wages for that first column, so if we run this line, it's going to tell us false. No, x1 is not a character. Is year a character? False. Is age a character? False. Is marital a character? True. So we have, this is the first character vector in this data set. And you can sit there and run that across like each one of these variables. But there's also a function called map, and what map does is it takes whatever function you put in it and runs it across each column of the data frame that you put into it. And so I'm only pointing this out. You don't need to know this. You won't need to use this ever for anything Bill ever asks you to do. You will not ever have to use map. If you are using map, then what you're doing is above and beyond what he's asking for. I'm simply pointing it out because I use map a lot and I use it for demonstration purposes, and so like I'll show some examples of things that can be done with it. But anytime I use it, just know that that's more so that I can show you a quick, easy glance of some shot of data, and that if you want to adopt it in your own analyses and things, it's there to mess with. But do not worry about using this. And again, if you are using map, then you're doing more than Bill is really asking for. But anyway, so like I said, what it does is it takes whatever function you put in and applies it across each column of the data that you pipe into it. So here, if I just have is.character as the function in map, and I pipe my wages data frame into it, it just runs that across each column. So x1 is false, year is false, age is false, marital is true, race is true. So just each column, it applies this function that I put into it here. Again, just to be clear, you don't have to know that. Let's talk for a minute about renaming variables. The function to rename variables is going to be intuitively named rename, and the arguments that you'll put inside it are some new variable name, what you want the variable name to be, and that goes in quotation marks, and then the old variable name, or you can use column numbers, although like I'm not a big fan of indexing by numbers. I'd rather use names, but it's possible, so I'm just letting you know because you might see it out there. And so, for instance, if we look at just what our column names are, and we have this x1 column, and if we look to see what that is, we can see that x1 column is just the it's a unique identifier. It's the participant number. So if we want to change that to p.num as our column name, then we take our wages tibble data frame, and we pipe that into rename, and we tell it our new variable name is p.num equals x1, and that's going to tell it that we want to rename the x1 column p.num. So if we run that, we can see that now x1 has been changed to p.num. Like I said, you can also do it by column number, and so instead, if we said we wanted to change education, the 6th column, to just edu to shorten it, we could do that as well. And again, notice how that now x1 is back to this first column because here I didn't store it, and same thing here, I didn't store it. I simply ran that one line, but it output this tibble that had the 6th column renamed to edu, but I haven't stored that new tibble as an object. So in order to store that and keep those name changes within the wages data, then you have to assign that, throw in the assignment arrow and assign that over that wages tibble. And now when we look at our call names, we see that pnum and edu are the actual call names in our data sets. Just as the base R alternative, like as far as like if you just look at call names, if you index by using bracket indexing, so if outside of call names wages I throw 2 in brackets, that's going to index the second column name or year, and so then I can assign an individual thing to it. So if I do this weird capitalization, because R is case sensitive, you can now see that that is now the name of the second column. The same thing can be done for renaming multiple columns. So here, if I index the third, fourth, and fifth columns, and I change that to just caps lock age MARR period for this one, and then capital RA lowercase ce. So if I assign those 3 things over to these columns, and then look at our column names, we can see again that that is stored there. And then just to get everything back to lowercase, if I take our column names, wrap it in a function called toLower, it conveniently converts all the characters to lowercase. And so if I do that and now look at my column names, I'm back to all lowercase column names. And so the reason that I point out this to you is because there may be times, especially if you have things systematically named, where it might be easier to select some vector of column names and apply some other type of function that helps with the systematic naming, and it's just going to systematically attach a certain letter or a sequence of numbers onto a sequence of variables and rename variables that way, and that may be easier sometimes than naming them one at a time with this rename function. So this is going to be the way that you'll want to do for naming individual things here and there, maybe a couple of few, but if ever you have big chunks of data, say it's like a specific scale that has a certain naming convention that you want to change, using something like this might be a little bit easier and a little more straightforward. So if you want to quickly table the counts of different responses for some variable, the most basic way would be to throw it in this table function. So if I just do table for wages $edu, so again going back to that base R notation, you can see that it tells me there are 268 that are less than high school graduation, 966 cases that are high school grads, 643 that are some college, etc. So here we just have a basic table of our counts. The tidyverse approach to this would be to, we could do it a couple different ways. We could start with our wages data frame and then select our education column. And so now if we take that education column and pipe that into table, it'll give us that same thing. So this and this, the output is the same, essentially, that it gives us that same count here and here. The difference and the benefit of doing it the tidyverse way is because it can expand in ways that this cannot. So for instance, if I take my my whole data set and then I use a select function that instead of just selecting one particular column, there's select underscore if, and so now it's just combining it with an if statement that if it is a character column, then select it, and then piping that into map and map that table function. Then what it's going to do is take my data set, select all of the character columns, and output the counts across each of those tables for each of them. And so again, not something that you need to know, because you can always, even if you had a problem that wanted you to lay out the counts for all this data, you could select one by one all of these columns and put them in table if that's what suits you. It'll get you the answer that you need, and that's all you need to know. But I just want to kind of point out that for the tidyverse approach in particular, it's there are some benefits that go above and beyond the base R way of doing things. So now let's look at if we change health into a factor. So here I'm just starting with piping it straight into levels, which is just the function that tells you the levels of some factor. And so this tells us that the levels are 1 period less than equal good, or 2 period space greater than equal very good, are the 2 levels. So I started here just by piping it straight into levels, just to look to see what how many levels there are, what's that default order, and things like that. So I'm cool with leaving this as like in this order of this group first and this group second, but I want to change the labels, and I don't want it to be labeled 1 period space less than equal good, and instead I'm going to change those labels. So I'll take that wages data frame, pipe it into mutate, because I'm going to mutate to change this health variable. And so what I want to do is I want to factor that health variable, but I'm going to change my labels to not so good and most excellent. And so if I run that line now, I'm highlighting to avoid that assignment arrow first. And you can see that it has changed my health here to a factor that has 2 levels, not so good and most excellent. So now I'm going to run the whole thing to assign that over this wages, and now when I take a glance or a glimpse, I can see that indeed it is a factor with labels not so good and most excellent. So here's a couple things to do just for practice to check out and see how you're doing. Using the wages data frame, change the variable pnum to ID, coerce age into in the heights data frame to an integer variable rather than a numeric variable. Create a factor from one of the character columns and give it sensible labels, and then find the mean and standard deviation of wage in for whichever factor you wanted to create above. So here it's all using those basic dplyr functions that we'll need, and I've told several people that you just have to absolutely know these few dplyr wrangling functions: the select, mutate, filter, group by, and summarize in particular. Those 5 functions you just have to absolutely know like the back of your hand, and understand how they work and how you use them, because with those combined you get all the data manipulation that you really need, and if you don't understand those 5 functions, then you'll really struggle to keep up with a lot of the stuff that we're talking about. So like this, for instance, is a good example of just using those functions. Bill has mentioned to me that some of you will are still using like a filter to break things down. So if I'm looking at this filter and I wanted to do something by the health variable, here, this not so good and excellent, that you would do filter health equals not so good, right, because I created it as a factor. Well, either way, point is that you would use a filter to filter things down based on something into a smaller group, and then you summarize to find the mean or standard deviation of that one group, and then filter the other group and find the mean and standard deviation with that other group, where what you need to be doing there is using that group by function. So you shouldn't ever have some data that you pipe into a filter x equals 0, and then that into summarize mean x, and then do the same thing for x equals 1, and we'll say this is mean y. So this is bad, and instead what you want to do is cut out this filter, and you're just going to group by x and then run that into that summarize function, and it'll give you the output for the group where x equals 0 and where x equals 1. It's going to give you that mean of y, but you're not filtering down to some subset just to get that summary statistic, when then you're going to turn around and filter back to some other group. And instead, again, that's one of those, group by is one of those functions that you just need to know. Moving on to the binomial distribution, there's different functions for this, but we're going to look at this dbinom. And the arguments in it are x equals, size equals, and prob equals, with x being the number of successes, size being the number of trials, and prob being the probability of success. So if we look at where for 2 successes out of 4 trials with a probability of 0.5, then it will return this 0.375. And again, here, just looking at reminding you that if things are in the right order for those default arguments, then you can leave off those labels and get the same result. So the probability of getting 2 successes out of 4 trials with a probability of 0.5 is 37.5%. If we put in this vector 0, 1, 2, 3, 4, what it will do is it will give us the separate probabilities for each of the possible outcomes. So the probability of 0 is 0.0625. The probability of 1 success in 4 trials is 0.25. Probability of 2 successes in 4 trials is 0.3750, etc. If you sum all those up, you'll see that the probability of all the possible outcomes is obviously 1. But if you sum up just some subset of possibilities, so in this case, instead of saying 0 through 4, we're just going to say 0 and 4 in that combine or concatenate function. And we can see that the summed probability of getting either 0 or 4 successes in 4 trials is 0.125. And then if we scale up to a larger sample size, let's say that instead of 4 trials, we have 10 trials. And we want to see the probability of 0, 1, 9, or 10 successes. So we will sum up the probability. If we run just that portion inside the sum and inside the parentheses there, it gives us the probabilities for each of those 4 things, and those 4 things being 0, 1, 9, or 10 successes. And then if we wrap that in sum, then it gives us the cumulative or total probability is 0.54. If the total probability of getting 0, 1, 9, or 10 successes in 10 trials with a probability of 0.15 is 0.544. There's another function, binom test, that will give you p-value if you're looking for p-values on things. So same thing here. If we look for the p-value of 9 successes out of 10 trials, where p is the probability is 0.5, then we can get our p-value, and we can see that p is 0.02. So assuming that you have an alpha of 0.5, this is one where you could call this that this is a significant finding here. The last thing we're going to do real quick is create a probability distribution, and we're gonna table it and graph it. So if we are looking at 10 trials, and we're using that same dbinom function, and we say that what is the probability for each between 0 and 10? If the probability is 0.5, what's the probability for each of those outcomes? So we're going to have that, and so we're going to create a tibble where x is 0 through 10, and then prob equals this function that we just now ran. So what that's going to do is put these 10 values in the prob column and the values 0 through 10 in a column called x. And so if we run that and take a look at it, we can see, yep, it's outputting what we want. Just a small note, I always recommend, don't start with assigning things, especially if you're writing over data and things. Always get the function to work and output the way that you're expecting it to be. Then go back in, put in your arrow, and put in that object that you're assigning it to. So now we're going to create this thing called probdf. And probdf is simply the x values 1 through 10 plus those probabilities of 0 successes, 1 success, 2 success, 3 successes, etc. So now if we take that and we put that into ggplot, and we tell it ggplot, we tell it our data equals this probdf that we just created, that we want our x value to equal x and our y value to equal prob, and then we add on a layer and tell it geom point just to get some points on there. Then here's what our graph is going to look like. If instead of running geom point, if we run geom line, then all it's going to do is use lines to connect each of those points that we just mentioned. Or we could do it as a bar using geom bar. And here the only difference is that we have to tell it, we enter this additional argument stat equals identity. If you don't use that, it's going to throw up this error because it will tell you stat count can only have an x or y aesthetic. And that's because the default summary statistic that bar is looking to compute is a count of whatever variable you put in it. But in this case, we're we already have the actual, we're not needing a summary statistic. We're looking for stat equals identity, which means I'm not wanting you to summarize the counts of this prob, the y variable, but rather the value itself, the identity, is the number that we're looking to, where the height of the bar should be the number specified in the column, not some summary statistic of the column like count or means or whatever. So all you need to remember is that when you're looking to plot bars, then you need to add stat equals identity like this. And then the last thing, if we take that and just add on a plus here and add on this one last piece, labs, I just wanted to show you that this is a real quick and easy way to change your labels of things. So again, this is what the default, it's just labeled as x prob and no title. And if we add this labs layer, then you can just tell it, whatever x equals, whatever y equals. If you leave something off, if I take off that x, it will just leave it at its default. But you just tell it, x equals, y equals, title equals. It'll even accept, subtitle equals something. You could run that, or it has caption equals something else. And then of course there are other arguments or other ways to then adjust the where these actually appear. So the justification, moving your caption over to this side, all that sort of stuff is all customizable. But I just wanted to point out that real easy way to get your labels and your title at least is just to use this labs layer and just tell it x equals, y equals, and title equals, and you can get all of those things plotted on there. So then for practice on these, find the probability of getting exactly 4 heads if a coin that is fair, which is that probability is 0.5, is flipped 20 times. And then what is the probability of getting 4 or fewer heads, or 16 or more heads if you flip it 20 times? So the total for 0 to 4 or 16 to 20, what's that probability? So that wraps up today's drill video. If you have any questions, feel free to shoot me an email, or I will talk to you on Thursday or Friday during drill.